My name is Fredrik Svan. I'm actually working at Ericsson, and with that, that's probably the last time you'll hear the word Ericsson in this presentation. What I'm going to present here has basically nothing to do with this company. But a few years I started in this company mid-90s, and been working with large enterprise scale products like the AXT301, which you've probably heard of. I used to be responsible for the basis of the AXT301, and I've been working with Erlang for more than 10 years. So I have some experience in that area as well. So, but this is not about a certain company. It's a bit of a hobby project that I did on the side. Well, it was more for my learning, really. So the outline, what I'm going to talk about today is, first I'd like to say a little bit about Erlang in the browser. What is it? So naturally, I thought, well, everyone will understand what it is, but I realize now that, well, it's maybe you can do Erlang in the browser in many ways. You can do it through a plugin, or you could do it as a JavaScript virtual machine, as I did, or you could do it as you could translate Erlang code to JavaScript, which is another project. A little bit about why did you do this? You must be crazy. Yes, probably, but I hope it doesn't manifest itself today. And also a little bit about the technical stuff, the things that you're probably interested in. Writing your own emulator, how hard can it be? I mean, probably most of you can do it. Some experience I had when I did this. And then a little bit about the current status and future plans, because this is an ongoing hobby project. So what is Erlang in the browser? It's a virtual machine that I've written myself in JavaScript. It's 5,000 lines of JavaScript, which makes it a kind of smallish program, really. It's a subset of the functionality in Beam. It doesn't aim to be a full virtual machine like Beam, so it's not competing in any way with the real implementation. It's purely based on reverse engineering. I haven't had access to any secret Ericsson documentation. I haven't actually asked anyone who knows about this stuff and who does it for a living. I actually made a point of trying to do it myself, because I wanted to show that basically anyone can do it with or without documentation. It understands the Beam file format, at least to the extent that I needed. It executes Beam opcodes, and Beam opcodes, they are like assembler instructions. They move things, turns from one register to another register. It can do simple switches. You could look, for instance, is this a list? And if it's not, then you branch somewhere else and do some other labeling work. There is actually an API for calling JavaScript functions, like eval style, if you know JavaScript. And you can also access DOM, the object model of the browser. So you could set things and you can change paragraphs and things like that from Erlang. Which is, well, that's kind of, the API isn't set yet, but I just wanted to make a sort of proof of concept that you can do this. You can talk to a normal node and normal Beam emulator, and I'll talk a little about the distribution. It's very rough at the moment. And there is actually a demo page on GitHub. All the code is available on GitHub under the MIT and GPL licenses if you want to use it yourself or contribute. So why did you do this crazy stuff? Basically, I wanted to learn something new. I wanted to learn JavaScript. I hadn't done anything in JavaScript. I hadn't written a single line of code in JavaScript. And I wanted to learn JavaScript. I also wanted to learn more about the Beam because I'm actually a big fan of the Beam. I think it's really interesting to kind of look at the inner details of the Beam and how it works internally. I'm not an expert in any way, apart from the little bits that I picked up everywhere. Basically, JavaScript is everywhere. It's on my Android phone, it's on my wife's iPhone, and I've tried to make it possible to run it on as many browsers as possible. But I think for me the main motivation is that it seemed like a funny challenge to do this. Well, this is a hobby project after all, and maybe someday it will be product quality, but it isn't at the moment. It's a start anyway. So, looking at the gory details, the technical details, basically this 5,000 lines of JavaScript can be divided into 4 parts. I've tried to separate them a little bit. So there's this Beam file loader, which understands the Beam file as they are compiled by the compiler, and it can unpack it and sort of change the data structure so they are easier and more efficient to read in JavaScript. It's a very, very short part of the program. There's the emulator main loop, which is sort of the heart of the system, where you chew the opcodes and you execute them one by one in a continuous loop. There are the built-in functions, and there are many of them, I can tell you. I'll talk a little bit more about that later. And finally, there's the distribution mechanism. The Beam file loader, that's really, was slightly tricky to reverse engineer. I had lots of problems in the beginning. Anyway, it can, as it is today, it can take an individual Beam file, or it can take a list of individual Beam files and load them one by one. And I quickly realized, because of the latency in the network, loading a single, like 30 or 40 single Beam files consecutively, that takes forever. So I built in a possibility to take a tar file of Beam files, and you load them all at the same time. So that's basically what I do with the files in the standard lib and kernel application. It uses a sourced in zlib compression library for the strings part of the Beam files. It uses type arrays, which is a fairly new construct in JavaScript. I'm not sure how much you know about JavaScript, but it doesn't work in all browsers. And when I say it doesn't work in all browsers, it usually doesn't work in Internet Explorer. So, yeah, there are some remarks in the code in some places about that. I will not talk more about that, but I had to implement a fallback to strings, which is not as efficient at all. So that makes it, well, loading Beam files is quite time-consuming in older browsers. If I look at the Chrome, basically any release of the Chrome or Chromium web browsers, it loads a system with a minimal profile in less than a second, and that's basically time up to where you have a prompt in the shell in your browser, and that's on my fairly lousy computer, which is 1.3 gigahertz, and it's a Intel Pentium, some kind of laptop processor. So So this is not a, well, high-end laptop at all. But it's quite fast to load in Chromium. In other browsers, it can take up to a minute. But other browsers have later versions which are comparable to Chromium and Firefox. It cannot do hot code loading at the moment. It's not a technical reason. It's more that I didn't find it actually quite interesting to implement it hot code loading, or because the sessions in web browser is usually quite short. So the emulator main loop, the heart of the system, it's a big, huge loop over a switch statement, a JavaScript switch statement. And for each call to a function, Erlang call to a function, you decrease the number of reductions that you have, and when the number of reductions reaches 0, you take another process and you start executing that in the same loop. And it handles some 120 opcodes today, more or less. I would say less when it comes to bit strings. I would say more when it comes to like the very basic operations. Most opcodes are 3 to 4 lines of JavaScript. This was actually, I've seen the discussion on the mailing list about reverse engineering, and especially when it comes to the opcodes and need for documentation. My feeling is that this wasn't actually very hard to reverse engineer compared to the beam file format, because well, the opcodes are quite beautiful in their simplicity. They are very logical. They do a very limited amount of things, and they are really, there is good engineering behind this. There is a lot of careful thought behind the opcodes. So they are actually, you can almost guess from the name what they are supposed to do. Some of them are a little more tricky, and like the reapply one thingy. I don't know today what it's supposed to do. You're laughing, Patrick, so you can talk about this on a beer later. We can also talk about some opcodes that seem to be obsolete, at least the compiler doesn't seem to generate them. I'm not sure about that, but yeah. Well, the built-in functions, that was the story here, is that if you're going to make this on your own, you'll have a lot of work to do here. And this is documented things. You know, you have the nice documentation that says this function takes this, and it sort of returns this thing here, over here, the list or something. But then there are the undocumented exceptions, which are used everywhere by people who know about them. And also, there are undocumented functions, very few of them actually, but it's a big surprise every time you run into it, and you don't really know what to do. And there is a lot of code here. This is the big part of the system. Like, for instance, ETS, the Erlang term storage. I don't know if someone actually has used all the functionality there. I mean, it's really, really tricky to keep up here, or to try to implement all the things here. And I haven't done that, and especially not for the term storage. It's a lot of work, and I think much of the work is also, to be honest, a little bit boring, like validating the arguments to function calls. Is this a list, and does this list have the correct format, and things like that. So that's basically, I've tried to program JavaScript the Erlang way, so if it doesn't, well, let it crash basically. And it doesn't quite work so well in JavaScript as in Erlang, I can tell you, but at least it's as fast to do that in JavaScript as it is to do it in Erlang. So if you do use the BIFs correctly, they will work. But if you pull them with the wrong stuff, they will not work. and will obviously never work due to limitations in the browsers, like GenTCP, GenUDP, file operations. For instance, the OS commands doesn't really work, doesn't really map or apply even to browsers, I would say. So, distribution mechanism, it's using sock.js to connect to a server. The client, the browser client, connects to the server using sock.js. And this is again code that I sourced in, both on the JavaScript side and on the Erlang side. It was readily available. And the messages that I passed are encoded in the Erlang external term format. At least to the extent that I managed to reverse engineer it. It's actually quite well documented, I believe. The server uses a proxy similar to the SSL distribution proxy that's available in OTP, and this makes it possible for me. The main motivation for me to do this was a proof of concept. I also wanted to basically run the test master, the common test master in Erlang node, and then connect to several browsers and run tests in several browsers at the same time. So all the examples here are in a file called tester.l that's available on GitHub as well. So basically what I do here is I have a browser or several browsers. Several browsers doesn't really work at the moment, but one browser we can do. And then it connects to a proxy, which translates from sock.js to the format that the emulator, the C code down here, expects. And the proxy is written in Erlang. And then it sends the signals to common test master and the other way around. So basically I spawn the test master in this normal Erlang node. And it will spawn a test client here up in the browser using RPC calls. I believe, I'm not sure actually how the common test master works internally, but must be. And of course there are limitations here as well, so you cannot have a fully meshed network between. So one browser can connect directly to another browser, which Erlang actually assumes, like global, I believe, assumes that you have a full connection to all nodes. So the experience is, as I mentioned before, I'm actually a big fan of the emulator as it is today. It's very heavily optimized. It's extremely efficient. The code as it looks today uses computed go-to, so you basically execute one. You don't have the loop that I have in JavaScript, and you execute the opcodes directly one by one. It has a lot of optimization, so it translates, for instance, the opcodes found in the beam files to internal opcodes, which are more efficient because you know more about the sort of data that you execute. This doesn't scale very well. I tried to do the same thing in JavaScript, but the JavaScript, at least the Chrome variant, has the bigger you make a switch statement, the slower the switch statement will be. So basically, that's currently how it looks like in Chrome. I believe that there are, the JavaScript version, the JavaScript machines are getting better and better. But at the moment, if you have like 5 opcodes in your sort of language or your assembler, then that will be 16 times faster than if you have like 120. Probably that's something about jump tables there or something like that. But implementing the BIFs, it's a lot of work, and it's actually quite hard, and for me it was also boring work. But you might have different opinions if you want to try this yourself, and I can actually recommend it. It was very fun. Error handling is hard. much of the stuff that when you run the OTP test server and you run the test cases that are supplied with OTP, and there are hundreds of them, you get a lot for free. You get a lot of regression testing for free. Error handling, I haven't really found a test suite that finds problems when you do error handling wrong. So that's, I'm not quite sure that I actually got it quite right. Bit strings, tricky. There's a lot of bit fiddling there. You can have things which are not aligned on the byte boundary, which the underlying storage uses. And the JavaScript engines differ a lot, and I'll leave it at that. Common tests, special thanks for that. It saved a lot of time in regression testing. All the test cases, there are hundreds of them. It's a huge, huge thanks for that, actually. It's a lot easier. Characteristics, bad news. It's factor 10 to 20 slower than the emulator, the normal emulator on the same hardware. And I was actually expecting a lot more or a lot worse. I mean, this is basically it's a script that I feed into a browser. It's not like it's the normal beam. It's been optimized for some 20 years now, and it's by some very intelligent people. So I mean, I think it's quite good to actually be 20 times slower than something that's being worked by so many people. BIF dispatch is significantly slower, and I know the reason for this, but if I would do something about it, it would make my code very ugly. So that would need to be done in some kind of optimizer or minifier or like a Google closure compiler or something like that, or some kind of pre-processor. So I don't really want to make the code unreadable in the way that would be needed for the BIF dispatch to be faster. Lists use more memory. I don't recall the exact figures at the moment. Maybe Joe, you remember our discussion. It uses more bytes than the emulator. It's 4 times more bytes than the emulator. Garbage collection is on system level, which is bad news. In Beam, it's more finely granular. I think it's on process level, which makes it a lot faster for a single process. And timers are, I wrote likely to be less exact. The correct phrasing would probably that they are less exact. Erlang now, for instance, the granularity of the JavaScript call for retrieving the time of day is in milliseconds. In Beam, it's in microseconds. But I still maintain the guarantee for Erlang now that it will continuously grow for each call, so you don't get 2 consecutive calls, you get the same millisecond return. And there are probably other things which you cannot really do in a browser that you can do when you have full control. So, near future plans, this I'm working on bit strings at the moment. The term storage is a huge undertaking. I've written some kind of stub code for that because some like timers and use the timer module uses sleep. It uses the term storage that had to implement some stub code there to make it a fully compliant term storage. It's I believe thousands of hours to do that. I'd like to make it fully compliant to the Erlang external term format. I don't think I can pass funds at the moment over the distribution protocol. Improving the pass rate for the OTP test suits. I've been running the standard test suite, and it's like 60–70% of pass rate. Much of the remaining ones are depending on the ETS again. I'd like to modularize it a bit more, especially if someone else is interested in contributing. I'd like to split out the loader so you can basically implement a more efficient loader, and you could like make a pre-prepared image of the system that you're going to load, and then basically load it and start executing right away in that code. Nowadays, I need to, the file format in the Beam files is quite abstract, so you need to do a lot of parsing before you can start executing. I'd like to split out X and the file driver because there's a lot of functionality and that's really stuff at the moment. And maybe it's not needed in all scenarios as well. Probably if you just want to run one single Erlang module, you don't need a file driver, you don't need ETS, quite likely. Make support for Minifier or some kind of like Google Closure compiler. That would be really nice. Also some kind of pre-processing for handling the atom table and stuff like that. More efficient BIF calls, I already mentioned that. And finally, make it more object-oriented. And I actually haven't written much object-oriented code in my career. And some people even doubt if JavaScript is really object-oriented. I think you could very much you could improve the encapsulation. You could probably make it possible to run more than one emulator in the browser. And there's code in the test suites that actually depend on being able to start a slave node for the test case to pass. The wild ideas. This is the fun stuff. I'd like to actually try to compile the Erlang code directly to JavaScript for functions and see how that compares. And in terms of memory and performance. Using the HTML local storage, this is basically a key value store which resides locally in your browser. So you could basically with this you could have a amnesia, you could have a persistence over sessions. You store things locally. This would probably make it possible to use the compiler in a more standard way. Multi-threading using HTML5 web workers. The last two bullets here, it's not going to work in all browsers, which was my main sort of aim in doing this. But this will certainly be very interesting to look into. You don't get the same thing as with key threads, but at least you get more than one thread of execution in a browser, which make it faster. A distribution proxy, I mentioned before that you can't connect directly between one browser to another browser. You could have a proxy for some kind of use case, which I don't know about, where you would proxy communication between two browsers. So you could have a sort of fully meshed network by that proxy. And finally, some kind of, I called it quick check style testing. I probably should have put these little things around the quick check, because it's, what I'm thinking of here is that, well, yeah, I have a node which I know behaves correctly, and I have another node which I'd like to test. And I can run the same thing on those nodes, maybe randomly generated data, and I could compare the results since I can then communicate. And that would probably be good for like testing binaries of bit strings. So show me the code. I won't do that here because it will take too much time. I only have 9 minutes left. There's a demo available here as well. So this part is a bit interesting. So first, I'd like to have contributions. And if you don't want to contribute, I think the very best thing is that you write your own thing or you fork it. Because the more people doing stuff, the more we learn as a collective about how it works internally. If you want to contribute, you must make it available under the MIT and GPL licenses, and it must be good quality code, obviously, so you mustn't make it slower and decrease the pass rate. I think if someone knows JavaScript, I think it's probably a good opportunity for optimizations, which some people think is the most funny thing to do. And there is also a lot of code to write. So thanks. Before I take the last slide here, thanks for your time. I was actually planning on, and since I have some time left, I was actually planning on showing what it looks like. So I have a normal Erlang shell here, which isn't connected to anything at the moment. Hopefully, no, it's not. And here is Google Chrome, and I connect to a web server which I have locally, and I'm running Cowboy here, but probably would work with basically any web server at Linux or Jaws or whatever. And then you could see here I got the handshake between the nodes, which is something I probably could have written it worked here. I'm hoping that's what it says. Anyway, and then you see I have a node that's come up here in the list of nodes, and this is a randomly generated name which is passed in the handshake. And then I can run my tester script, and this will start the common test, which will connect to all the nodes here in this list of nodes. And it will start the common test client here up in the node, and then it will start, the common test client will start running the test cases, and they will be reported back to the test master. So these are the events going through the test master. And it says error normal, but it also says here that all the test cases have passed. And this is the array suite, which was it's mainly using tuples and lists, so it's fairly basic functionality. Timers, for instance, has three test cases failed, which due to using the term storage. So with that, I leave it for, do we have room for questions? 5 minutes maybe? 5 minutes questions? So, who will be first? Do we have a mic? Patrick, you promised to be nice now. Yeah. Remember that.
Wasn't this really hard?
Yeah, you should get a higher salary. Very tricky stuff.